fundamental theorem of calculus. This is something that's pretty darn easy. It's going to give us a way to evaluate definite integrals. So remember the indefinite integrals, you integrate it, you got to remember the plus c. But now we have a definite integral, which these will have the numbers attached to it. And so we won't have a plus c on these answers. We'll actually plug it in, use this fundamental theorem of calculus as f of b minus f of a thing I'm about to show you, and we'll get a number for that integral. So we're going to evaluate the integral with the numbers attached there. That's what this fundamental theorem of calculus is going to allow us to do. The fundamental theorem of calculus has a couple other parts too there, and we'll review some more when we do our AP review in a little bit. But main thing is just evaluate a definite integral for now. So when you integrate something, you're going to integrate the function, right? Use your shortcuts, get your antiderivative, get your integral, and then after you integrate it, we're going to stop. We're going to make like this little bracket thingy, and we're going to evaluate that thing from A to B. And the way you do that is you take the top number and plug it in. Those are called your limits of integration. So you plug in your upper limit of integration, plug it in, and then you take the bottom number, plug that in, and you just subtract those. So when you have a definite integral, you integrate it, no plus c, plug in the top number, plug in the bottom number, subtract them. That's your integral answer right there. So let's do a few examples. All right, so when I integrate this guy, so it's going to be 4. Carry down, you're going to go integrate that using an easy power rule there. So you're going to go x to the 4th over 4, and then those will cancel out. And now you have x to the 4th, that's your antiderivative, that's your integral answer. And now we're going to plug in the numbers. So since we have a definite integral, no plus c, we're going to plug in the 2 and the 5. So I'm going to make this little bracket thingy. And when you evaluate a definite integral, the fundamental theorem of calculus says you take the 5 you plugged in for x, so you're going to get 5 to the 4th, minus, take the 2, plug it in for the x, get 2 to the 4th. So you get a number for the top, get a number for the bottom, and then just subtract those. That's going to give us 625 minus a 16, which is going to give us 609. And that's our integral answer. Now, remember what the integral is going to start. Remember, derivative is slope, integral is area. This actually gave us the exact area underneath the curve. If you remember your main definition of your integral notes, remember this gigantic example here where we started with this function here. We did all this work. Look at the answer we got, that's 609, 609. You have to appreciate how powerful that integral symbol is. It just did all of that for us in a matter of seconds. So this is just a gigantic shortcut that we can use. And the integrals will get more involved, but when you plug in the number part, you just plug in the top number, plug in the bottom number. Now, the reason that gave us the exact area underneath the curve, because again, when you graph that 4x cubed in between 2 and 5, that entire graph was above the x-axis, right? If the graph goes below the x-axis, we'll make that connection in a second here. But you gotta be a little bit careful if the graph is ever going below the x-axis. All right, let's do another example. Just pick one on purpose that was just a little bit messier with the fractions and stuff there. So the first thing I always do is if I have a constant, I'm gonna pull that constant out in front and rewrite it like this. So we have x minus x squared. I'm also gonna get rid of that radical, just because it can be x to the 1/3. And then you have a monomial. So remember, when you have a monomial, you can do it that over that, that over that problem. So that 1/2 can stay out there. And when you do it that over that, that's going to be a 3/3 minus a 1/3. So this is going to give us x to the 2/3. And this is a 6/3 minus 1/3. That's going to be x to the 5/3. All right, so you do it that over that problem. And now you got to remember to integrate that thing. So the 1/2 I'm going to carry down in front. Just leave that out in front, those extra constants there. Sometimes when people distribute that, they make things a little bit too complicated there. But you're going to integrate this. You're going to go x, you're going to add 1 to the exponent. So that's going to be 5/3. And then you're going to divide it by 5/3, which is the same thing as multiplying by the reciprocal to get to 3/5. And same thing, you're going to add 1 to that exponent, use your easy power rule. So that's going to be to the 8/3. And then you're going to divide it by 3/8, which means you're going to times it by the 3/8 right there. So there you integrated it like we did when we learned our easy power rule. And now after you integrate it, now since you have numbers attached, now you're going to stop right here. And you're going to evaluate this definite integral by using your fundamental theorem of calculus by applying your f of b minus f of a thing right there. So it's just a little bit messier than the prior example there. But what I'm going to do, I'm going to leave the 1/2 out there. And then you don't plug the 1 in for this one, 8 in for this. Sometimes I see some weird mistakes on this. You got to take the -1, plug it in for both those x's. Get that right there. And then you go minus, take the -8, plug it in for all of those x's, and then keep that stuff in parentheses because you're minusing a whole unit right there. So when I do this, when I plug in the -1 to the 5/3 times by, I'm going to get a -3/5. By plugging a -1, q to the -1 was -1, but you raise it to the 8th power, which is going to be a positive 1. So then it's just going to be minus 3/8 right there. So notice I took the negative 1, plugged it in for both of those x's into that function. There's that first part. And then you got to go minus. Now, when you're minusing something, this stuff has to be in parentheses. You're going to take the -8, plug that in. So that's a cube root of -8. When I go -8 to the 5/3 and I don't have a calculator, because most of the AP tests is without the calculator, so we got to be able to handle that with and without. But cube root of -8, do that bottom number first, right? You don't go -8 to the 5th without a calculator, and that number gets a little bit too large to do a cube root of that. Do the cube root of -8, which is a -2. Then you raise it to the 5th power. So this is going to give us like 3/5 times a -32. And I'm going to go minus the 3/8. And I'm going to do the cube root of -8, which is -2. Raise it to the 8th power. It's going to be 256. All right, now you got several options here. Sometimes if I see that things are going to cancel out, I might go ahead and distribute stuff and then cancel some things out. But I just like to plug in the -1, get a number for that. Plug this stuff into the calculator, get a number for that. So if I get a fraction for this, it gives -39/40. Minus, if I get a fraction for this, be -576/5. Minus a negative, you know it's going to be plus a positive. And so when you do all that stuff in the calculator, you're going to get this. And then you multiply that by 1/2, and then we get this as our exact answer right there. So we should be getting exact answers with those fractions, not decimal or anything estimated right there, but get that exact answer like that. And there you go. There's just evaluate that integral right there. So integrate it, just basically just a review of what you already know how to do. Nothing really new other than plugging in the top number, plugging in the bottom number. There you go. So I got an easy example, got a harder example, and then let's go to our friend trig. We're almost done here. Hopefully you remember from the trig integrals, you could technically do the integral of tangent squared plus the integral of 1. But see, when you integrate tangent squared, when you look at your integral list that we're supposed to know really well, there is no integral of tangent squared. You can't go straight to the answer on an integral of tangent squared. So what you use is the Pythagorean tangent. When I see this tangent squared plus 1, I'm going to make that secant squared, because tangent squared plus 1 is secant squared. There's your Pythagorean identities right there. And then notice the reason that was pretty nice is because we can integrate secant squared. The integral of secant squared is just going to be tangent right there. So I recognize the Pythagorean identity, and then we're going to integrate that. That's tangent, because the derivative tangent is secant squared. But look, you have a definite integral here, so we're not putting a plus c. You have to stop right here. We have to evaluate this integral from pi/6 to pi/4. So your fundamental theorem of calculus simply tells us plug in the top number minus plug in the bottom number. And then you should know the exact values of your trig from your pre-cal day. So tangent to pi/4 is 1. Tangent to pi/6 is the same thing as sine over cosine. So that's 1/2 over radical 3/2, which is 1 over radical 3. And then when you do your definite integrals, you don't have to waste time here getting common denominators in one single fractions. Once you get your definite integral, just plug in, get your exact answer. If you see you can combine some things, go ahead and do that. But you're allowed to just leave your answer like that, have that exact answer. Remember, we got one single fractions and common denominators and stuff like that when we did derivatives, because we use those to find the maxes and mins. But once you get your answer, we just want that exact answer, and then we're done there. All right, let's talk about the pretty important conceptual understanding part. This is the last thing we got to talk about, and this video is done. But I need to make the connection between the integral and the area. They're not exactly the same thing. You use the integral to find the area, but they're not exactly the same thing. So you might want to jot a couple things down, because I'm not writing everything down, but I'm going to say some important stuff here. The integral and the area are the exact same thing if your graph is above the x-axis. All right, but if your graph goes below the x-axis, your integral answer will be negative. But numerically, it's going to be the same number answer of the area. So if your area below the x-axis is a +5, your integral answer will be a -5. So if I just make up a couple numbers, I'm going to say the area of this dome-shaped thing that's above the x-axis, I'm telling you that that area is equal to 12. I'm going to tell you the area of this thing, little portion of below the x-axis, I'm going to tell you that that area is equal to 3. And so if I were to say what's the integral between 0 and 7, notice that the graph between 0 and 7 is equal to is above the x-axis. So if the graph is above the x-axis, the area and the integral are the exact same thing. So if the area is equal to 12, the integral is equal to 12. And then the difference is in between 7 and 10, that area is equal to 3. Area is always positive. So the total area of this is going to be 15. The area of that little bottom portion is equal to 3. But if I just ask you for the integral is, you're still going to use the 3, but if your graph goes below the x-axis, your integral answer will be a -3. So that's really all I got to know. So if they ever tell us the area, like a lot of times on the AP test, they'll give us a graph and we got to use geometry to find certain areas, and we just have to know, okay, if that was above the x-axis, boom, make that positive. If that was below the x-axis, boom, make that negative there. So there you go, area is 3, so then I know the integral is a -3 since the graph is below the x-axis. And then your integral is like the net result, okay? So if you want to integrate the whole thing from 0 to 10, +12, -3, your whole integral is going to give you a +9 right there. So it will give you that net result, and you don't have to worry about that. It'll just do that automatically for you. And then if you do want everything positive, if I put absolute value bars around there, because we'll do certain things in the future with displacement told as a travel, there'll be a difference between this and this. But the absolute value, you know that just by taking your graph and it's actually moving it above the x-axis. So the absolute value of f of x is flipping that pink portion that's below, flipping it up, and the area is still 3. But since if your graph is above the x-axis now, then that's just going to be 12 plus a 3 to get to 15, because the absolute value makes everything positive, makes everything above the x-axis, which means the integral answer is all going to be positive right there. So that's the connection between the area and integral. So just remember, derivative is slope, integral is area, and if the graph goes below the x-axis, then that integral answer will be the negative of that answer right there. So just in general, the first couple we might give you a couple problems towards the beginning of the homework where we might just give you a graph. We might give you something that you can't integrate yet because it's just a little more of an advanced integral we're going to learn in the future. But if I just say is the integral answer positive, negative, or 0, what you could do is graph the thing and look at that graph. And then if I notice that the majority of that graph is above the x-axis, I know that integral answer should be a positive answer right there. But that bigger part was below the x-axis, then my whole integral would have been a negative answer. Or if you have an equal amount above and below, a lot of times that happens on the trig problems, that integral answer will actually be 0 right there because you have an equal amount of area above and below the x-axis right there. All right, so there's your fundamental theorem of calculus, the first part. Where there is also something called a second fundamental theorem of calculus that we'll talk about in the future.